In this video, I'll be discussing the basic process of balancing chemical equations. So the first thing here to remind you is that when a chemical reaction occurs, it has to follow the law of conservation of matter, which means that you have to have the same number of atoms in your reactants as you do in your products. And so I give you an example here, the combustion of methane gas. We have, if you look at the black atoms represent the carbons. There's one carbon on the left-hand side, the reactant side. There's one carbon on the right side, on the product side. If you count the hydrogens, there are 4 hydrogens on each side. Those are the little white dots. All right, and then the oxygens are the red atoms. All right, and there are a total of 4 oxygens on each side too. And so the idea here is however many atoms of each element you have on one side of the chemical reaction, you have to have the same number of atoms of that element on the other side. And the reason is because atoms don't get destroyed within a chemical reaction unless it's one of those weird nuclear reactions which we don't really talk about in this class. So if an atom isn't getting destroyed, it's just the bonds are changing form, then if a carbon atom exists on the product side, it has to have existed on the reactant side. If you've got, in this case, 4 oxygen atoms in the reactant side, then there should be 4 oxygen atoms in the product side. It's just kind of switching what is connected to what or what is bonded to what. If you don't have this, it just doesn't make physical sense for the reaction to occur because you'd be creating atoms out of nothing or you'd be destroying atoms. And again, that's just not something that happens in normal chemical reactions. So the first thing here, when you're balancing a reaction, what you're really doing is you're changing the coefficients within the chemical equation to try and make sure that there are the same number of atoms of each element on both sides. It's important that you don't change subscripts, which are the little numbers that are written below, because if you change the subscripts in a substance, you're actually going to change the identity of that substance. For instance, H2O, you should hopefully know by now, H2O is water. All right? If you switch that H2O to H3O, we'd have something different, something that was no longer water. And if in a chemical reaction you know, for instance, that water is produced, all right, you can't just change what that subscript is because it would change what the element was. So we only change the coefficients. We only change what's up front. To remind you of what that is, that again, that coefficient is up front, the subscript's down below. We're only going to change the number up front as we go through this. Also reminding you how to count these things. Coefficients distribute to the entire compound, all right? So that 2 in front of AgNO3, that means we have 2 AgNO3s, 2 whole things. And so if you count that, the number of silvers that we have are 2 silvers because we've got 2 whole AgNO3s. We also have 2 nitrogens, and then we have 6 oxygens because each of those AgNO3s has 3 oxygens, and we have 2 of them, so we have 6 altogether. This is just doing some practice at how we count things when it's a chemical reaction because we're going to be doing a lot of that. Next, generally speaking, in balancing, there's just these couple steps that you're keeping in mind. You count the number of atoms that exist on each side. All right, how many are there on the reactant side? How many are there on the product side? And then you look at that and you change the coefficients on the front of each substance until you have an equal number of atoms of each element on each side. So that is the basic process for balancing. On this slide, we're going to do just a little bit more of that practice, counting how many atoms there are in each thing. So go ahead and try and figure out how many atoms there are, for instance, in this SiF4, how many atoms of each element. If you need to pause the video, pause and try and figure it out for yourself, and then I will go through the answers momentarily. Okay, so on the SiF4, that's just 1 silicon and 4 fluorines. All right, the subscripts just tell you how many they are. And actually the next one works out just as easily. All right, H3SbCl6 means that there are 3 H's, 1 antimony, 1 Sb, and 6 chlorines. And so the deal is this 3 just applies to the H, the 6 just applies to the chlorine. All right, the Sb, it has an imaginary subscript of 1. There's only 1 Sb. All right, that's how that works. This next one is getting a little bit trickier because we have this set of parentheses and then a subscript of 2 below. All right, if the subscript of 2 is applying to everything within the parentheses. So what this says is we have a calcium here up front, one calcium, but then we have two nitrates. And if we have two nitrates, two of these NO3s, that means we have two nitrogens and 6 oxygens. All right, so in the case of a subscript that falls on the outside of a set of parentheses, the subscript applies to everything inside of the parentheses. And so that 2 on CaNO3 doubles everything within the parentheses. If you have a coefficient, it doubles everything in the entire formula. So we've got 3Na2SO4 as this example. So if you count that, it's doubling everything. So Na2, there would be 2 of them, but we're, tripling it. It's tripling everything because it's a coefficient of 3. So 3Na2SO4, that's 6 sodiums, 3 sulfurs, and 12 oxygens because the coefficient triples everything within the formula. Hopefully that makes sense because we're going to be using this process of counting atoms quite heavily in the next step of this process. Going on to the next section of your notes here, I've given you a few tips that will help you in terms of balancing things. And so some reactions can be really complicated, and so what you're going to want to do is start by balancing the elements which are only in one compound on each side of the equation, all right? Because if they only appear in one compound, this should say compound, if they only appear in one compound on each side of the chemical equation, that's going to be easier. It's less fuss. I'll show you some examples later of some things where, you know, there's oxygen, say, in every single compound in the thing, and so then you'd want to leave that until the end. The other thing is, if you have elements that occur by themselves in a chemical reaction and they're elemental forms, like something that's like just iron or just oxygen or something like that, leave elemental substances until the end too, because you can kind of just write in whatever number you need at the end and figure that out. A last tip here is sometimes if you have a polyatomic ion, which are those ions that are listed on the back of your periodic table, and you're trying to balance, sometimes it works to just leave the polyatomic ion together as one unit, and I'll kind of talk about how that works as we go through some of these examples as well. And then sometimes you need to split up that polyatomic ion so you can't leave it together, and so that just doesn't even work sometimes. Okay, now I'm going to go to the bottom here of this page and explain this process of balancing. And so the first thing you need to do is you need to count how many atoms of each element there are. So this one only involves sodium and chlorine. On the reactant side, on the left-hand side here, we've got 1 sodium, as is written, and we've got 2 chlorines because it's Cl2. If we go over to the product side, with sodiums, we have 1 sodium and we have 1 chlorine. All right, so we can see here that it's not balanced because the left-hand side has 2 chlorines and the right-hand side has 1 chlorine. And so we have to add a coefficient to try and fix this. All right, so we can put a 2 here. The problem is when we put a 2 there, it actually doubles the sodiums and the chlorines. All right, so we have 2 and 2. All right. Easy to fix this though. If you look over on the left-hand side, we've got sodium alone here, and so you can just throw a 2 in front of that sodium, and it just doubles the sodium in that case, and we end up getting 2 on this side. And once you have the same number of each element on each side, you are good to go. All right, so this one is balanced now because there's 2 sodiums and 2 chlorines on each side. This next one's a bit more complicated because we have some more elements in here. We've got calcium, we've got fluorine, we've got hydrogen, and then I just tend to leave SO4, which is a polyatomic ion, as sulfate. I tend to just leave it as 1 unit here when we count it, and it occurs on both sides. So we've got calcium, fluorine, and then I write these in the same order on both sides as well. Hydrogen and sulfate, SO4. Okay, so when going through this, I'm going to just do the same thing. I'm just going to count what's on each side. Calcium's on the left-hand side, there's 1. Fluorines, there's 2 fluorines. Hydrogens, there's 2. and then the sulfate, SO4, there's only one sulfate here. If you had multiple sulfates, this is what it would look like. You'd have like a set of parentheses and 3, then that'd be 3 sulfates. All right, but we only have one sulfate here, so there's just one SO4. That 4 is part of the sulfate. All right, going over to the other side, calciums we have 1, fluorines we have 1, hydrogens we have 1, sulfates we have 1. And so if you look, you can see that the things that are unbalanced are fluorine and hydrogen. So we have to try and fix that. There's actually a simple way we can fix it for both elements, though. If you put a 2 here in front of this HF, it doubles the fluorine and the hydrogen on this side. So that's 2 and 2. And then we've got, you can see, a balanced chemical equation because it's got the same number of atoms of each element on both sides. For this next one, we've got carbon, we've got hydrogen, and we've got oxygen. Carbons, on the left-hand side, there's 1. Hydrogens, there's 4. Oxygens, there's 2. Going over to the right-hand side, carbon and hydrogen and oxygen. Again, there's 1 carbon. Hydrogens, there's 2. Oxygens, there's 1. All right, so carbons are good. I'll try and balance the hydrogens next. In order to do that, I need to put a 2 here in front of the H2O. If I do that, it modifies both the hydrogens and the oxygens, and so we end up having 4 hydrogens and 2 oxygens. All right, and in this case, oh wait, I miscounted the oxygens originally because if you look, there's oxygen in this substance and there's oxygen in this substance as well. All right, so there's actually now a total of 2 oxygens coming from this O2 and 2 oxygens coming from the H2O because there's 2 H2Os. And so we have a total of 4 oxygens here on the product side. All right, so we need to fix oxygen still. To do that, we can simply put a 2 here. All right, and get now 2 O2s. So there's 2 oxygens in an O2, and there are 2 of them, so there's a total of 4 oxygens there. And everything should be balanced in that one. Next one, we've got K, we've got Br, and then we've got H, and PO4 is phosphate. It's a polyatomic ion. I'm going to leave it kind of as one collective unit there. So potassium, on this side there's 1 bromine, there's 3 hydrogens, there's 1 phosphate. On this side, K, Br, H, and PO4. There are 3 potassiums on this side. For bromines, there's 1. For hydrogens, there's 1. For phosphate, there's 1. All right, so the first thing we're going to do then, it looks like the potassiums aren't balanced, so I can put a 3 on this side to balance the potassiums out, but that triples the bromines as well. So we end up with, oops, that was a 3 here. We end up with 3 potassiums and 3 bromines. All right, then we look over at the other side. Now we've got the potassiums balanced, but the bromines are off. So I put a 3 here in front of this HBr. What that accomplishes is then we've got 3 bromines and 3 hydrogens on this side because it switches both of them. And then if you look, we kind of weren't trying there on the hydrogens, but they sort of worked themselves out. And now everything is balanced on both sides. For CaCl2, all right, CaC2, we've got Ca, we've got C, we've got H, and we've got O. Calcium, there's only 1. Carbon, there's 2 of them. Hydrogen, there's 2 of them. Oxygen, there's just 1. On the other side, Ca, C, H, and O. For calcium, we've got 1 calcium. For carbon, we've got 2. All right, for the hydrogen, we've got hydrogens here, and we've got hydrogens here, so there's a total of 4. All right, and then for the oxygens, there's just, in the CaOH2, there's 2 oxygens in there. So looking at this, calciums are balanced, carbons are balanced, hydrogens and oxygens are not, though. All right, so here's what we can do. We can take, to get the hydrogens balanced, we want to get twice as many hydrogens on this side. All right, so we put a 2 there. All right, that changes this to 4 and 2. All right, and that actually, if you look on both sides now, has made us balanced with all the other elements. And so that is the general process. I'm going to go through actually here in a second a couple problems from the worksheet that we did in class. And so I won't go through all 50 of the problems on the worksheet, but I'll give you some general ideas. We tend to do most of this counting in our heads later on. And so you just got to kind of look at both sides and see how many of each element there are rather than explicitly writing it down. So this is the worksheet on balancing chemical equations. As I said, it doesn't leave enough room for you to go through and explicitly do it, but you can still kind of count on each side. So what I start with here is, like in the first one, I see that there are 2 hydrogens on the left-hand side and 2 hydrogens on the right-hand side. So hydrogens are good for right now. However, there's 2 oxygens on the left-hand side and there's only 1 oxygen on the right-hand side. Unfortunately, the only way that I can work this out is by throwing a 2 as a coefficient here in front of the H2O. If I do that, then what I get is I've messed up the hydrogens a little bit, but I can save the situation by putting a 2 there in front of the H2 as well. And so now we have 4 hydrogens on each side and 2 oxygens on each side. With this next one, sodiums, I've got 1 on the left, I've got 1 on the right. Chlorine, I've got 2 on the left, I've got 1 on the right. And so to balance out the chlorines, I put a 2 here, and then again, it accidentally threw off the sodiums, but it's okay because I can fix it by just putting a 2 there in front of the sodiums. N2O4, this one is actually pretty easy. There's only one thing on each side. You just throw a 2 there, and it balances the nitrogen on both sides, and it balances the oxygen on both sides. I'm going to jump down to a problem that shows a common situation that happens when you're going through these. So there's a strategy sometimes. If we've got, for instance, I'm just looking for one here where it works out. Let's see here. So for instance, number 11 here. When you're trying to balance this out, sometimes it happens that you end up with something here, something like this here, where we've got 2 iodines there and we've got 3 iodines there. When you're trying to balance the iodine, things get a little weird because it's hard to come up with a common multiple between 2 and 3 with just one coefficient. And what ends up happening is you need to do something which is called a 3-2 switcheroo, which is just a fancy name or like a silly sort of name for switching the coefficients and the subscripts so that you come up with the same common multiple. And so what this is in this case, for the Ni3, there's a subscript of 3, so I'm going to write a 2 up front. And that means there's 6 iodines there. For I2, there's a subscript of 2, so I'm going to write a 3 up front. All right, and that makes it so that there is 6 iodines in that one as well. And so sometimes you encounter this situation where we have 2 of an element on one side and 3 of an element on the other side, and you kind of switch the subscripts with the coefficients, and it helps to get it balanced there. I'll kind of show you another example of that as I find it here. Let's see. Maybe on the second page. I'm sure that there are quite a few examples of this. I'm just kind of going through and looking for one. So, for instance, I think, let's see. Oh, no, not that one. For being such a common thing, it's taking me a second. Sorry to find it here. Alrighty. Okay, here's an example on problem number 29. So we've got 2 F's here, we've got 3 F's here. And so to balance it out, I put a 3 in front of that F, in front of that substance. I put a 2 in front of that substance, and it balances the F's out that way. So that's called the 3-2 switcheroo. And then sometimes it even happens with bigger numbers. I had seen when I was going through and checking for this, for instance, here's a 2 and a 5, all right? And so balancing out a 2 and a 5, it works under the same principle. I can put a 5 here and a 2 here, all right, and get those oxygens to balance out, 10 oxygens on each side. And so it's a way of coming up with sort of a common multiple there, and it helps to do that. So those are some just basic skills there. This entire worksheet, you can find the key online in a PDF form, and so hopefully you've seen enough examples of the balancing that you kind of have a good grip on it, but if not, go ahead and try and look for the solutions to this and work them through and check your answers. And if you have any questions on balancing, you can come in and ask. There are also a lot of other YouTube videos that you can find online. If you just search balancing chemical equations on YouTube, you can find some things there, and that could help you out. So there are a lot of resources at your disposal. Make sure you take advantage of those.